to be here, and it has been a pleasure to have to put together the material I'll show here, which I finished late last night. So I hope that it will run smoothly. I will check your eyes and try to understand whether I did a good job or not. So what I'm trying to do is to pull together 7 or 8 works we've done in the last 8 months to try and provide you with some ideas of what you can do with body cameras in your area of application. So I will not show much of specific applications. I will show you tools that you can use if you want to use body cameras to understand the environment and to understand what the person is doing. So body cameras are pretty interesting because unlike fixed cameras we have seen in a number of presentations today, and we have been working quite a lot in the past, they are moving with the person, and therefore they provide you with a special viewpoint of the world. And at the same time, they provide you with information about what the wearer is doing. And there are a lot of applications that can be generated out of that. So it's a BMVA event, so I will talk primarily about vision, but in a couple of parts of this presentation, I will talk about audio and vision, and IMUs, so other type of sensing modalities that are available in cameras and vision. The structure of the presentation is as follows. We will start talking about how to track simultaneously multiple targets that are seen by a camera that is moving. And then I will move on and talk about how you can re-identify people you have seen from a wearable camera. So in an event like this, we would like to have a diarization of what happened during the day, maybe to recall a conversation or to understand how social we are or how social we are. And to do that, we need to understand maybe the color of the clothes, but if we are seeing each other under the slide, it might be different than the light we have in the corridor, which might be different from the light we have outdoors. So we will use audio to compensate for this variability. And in these 2 parts, I will talk about what you can do with body cameras when the cameras are looking outside the environment around. In the last 2 parts of the presentation, I will look at what you can interpret of the movement of the person wearing the camera. So we'll have a look, in between inverted comma, at what the person is doing, walking, running, going up the stairs, sitting, and so on and so forth, using the information from the camera. So the global motion of the camera worn by a person can provide you with information, whether moving left or moving right, I'm sitting down or going up the stairs. And since all of this could be pretty invasive of privacy, at the end I will explain some of the recent work we have done to define feature architecture, actually to learn feature architectures that allow you to do activity recognition or some classification problems that you're interested in while suppressing private information you might not want to disclose. And feel free to interrupt me anytime you like. So the starting point is, well, I'm wearing a camera, I'm going around, and in some cases you will see cameras on people, in some other cases you will see cameras on robots. So first-person vision for what we are doing in my lab is similar for people and for moving robots. So these are results from an international challenge that we have produced without using any appearance information. So the tracking results you're seeing here are tracking results that are generated only using the size and the position of the bounding box after we are given the results of our person detection. The method works online. It works in real time on a small Jetson platform. And we use that for UAVs and other type of robotic applications. This is another example with lower quality images. The idea is to have an understanding and awareness of the people around you so that, for example, if you're a robotic platform, you know what is your path, or if you're a person interacting with other people, you understand how people are moving around you. And again, this is the results of a method that generates first bounding boxes for people, and then color the boxes through tracking. And if the color of the box remains the same over time, we're happy. If not, well, we'll have to go back and redesign the algorithm. Who has experience with multiple target tracking? Okay, a few people. So you know that this is a rather difficult problem. You could see multiple target tracking as n times single target tracking. Nobody forbids you to do that, but however, you will lose information about the presence of the other target. So what we are really interested in when we do multiple target tracking, like in this case, is to start from a set of observations that are the bounding boxes that your classifier generates. We have seen in the first keynote this morning, you might have cars, vehicles, bicycles, any objects you're interested in. You might be provided with a position, with an height, and when you have multiple objects, you will have a set of observations that will change over time. You might have 5 objects now and 10 objects in a few seconds, 0 objects later on, and so on and so forth. Once you have generated over time this set of observations, multiple target tracking aims at generating trajectories, so estimating the state of these objects, so that in addition to cleaning up the position, cleaning in the sense removing some noise that might be associated to this observation, you will associate to these observations the identity over time, such that you can generate trajectories and you can obtain information about how the moving objects are operating in the environment. Something that is particularly challenging and interesting in multiple target tracking is that these two numbers are actually random variables. So we have 2 sets we are operating on that are whose cardinality is a random variable that changes over time. So we can of course say, well, n with k is 100, m with k is 100. We allocate the memory, we play with that, there is no problem with that. But actually we would like to have this set whose cardinality changes over time, and we can operate between the two in a very formal and straightforward manner. If you are familiar with the Bayesian tracking, on the left you have the formulation of the state transition and the observation model for single target tracking. And what we will be interested in is to have a similar formulation for multiple target tracking so that we can use the mental models we have for single target tracking for multiple target tracking as well. And I will use some formalism that has been defined around 2000 by Robert Mahler from Lockheed Martin, that has been defined for radar tracking, that in the lab we have taken and then extended to deal with the videos and extended tracking. So, what is the parallel between the two? Well, if this is the state and this is the observation, when we're talking about multiple targets, we have here the set of states that is coming from the set of state of the previous frame and everything that we have missed, the observation that are generated by the current objects, plus everything we have missed. And we can use this formulation in the same way we use the single target tracking formulation with a prediction and update. What is important here are just these two functions. So here we have the prediction, which is the set of the states at time k, generated as a function of all the observations up to time k-1. Then you have the new observations coming, you do your calculation and you generate the posterior, which is your set of states, using all the information that you have had up to this time. Right? And if you ignore the way this is formulated, this is very similar to the single target tracking. So what we have, to summarize, is we have an object detector that generates your observations. What you want to have is your states that are nothing else than your tracks. When we are dealing with multiple target tracking, what we want to be able to model is when a target starts, when a target ends, which is not a trivial task to make, because you can make mistakes, and therefore you could initialize a target in the wrong way, which actually was a missed observation for another target, and so on and so forth. And this formulation here is extremely elegant because it allows you to model very simply how a target is starting, how a target is terminated, and especially it allows you to model clutter and misattentions. And we'll see what is the exact formulation in the next slide, and I promise it's the only slide with formulas. However, if we use this the way we use a particle filter, for example, through a Monte Carlo approximation, the dimensionality of the state will grow exponentially with the number of targets. So it means that what I wanted to do earlier, meaning having my multiple target tracking on a small platform that I can put on my chest or on my head or on my glasses, is not really going to work. So what Mahler did with this formulation was to say, well, instead of propagating the full posterior, I will propagate the expectation on the posterior. And that's the probability hypothesis density filter. What the expectation on the posterior does is provides you with the number of targets in any decided area of your state space. So the PhD filter is a pretty effective spatial temporal filter that, however, loses something, right? So you're not propagating the full posterior, you're propagating the expectation on the full posterior. So you have very good properties, but you miss the most important thing in tracking, which is the identity. So the PhD filter is fantastic to clean up the mess that a detector can generate, but is not capable of propagating the identity, and we will see later on how we do that. I will now, in the next slide, if you don't like what I've just said, just switch off for 2 minutes, and then I will recall you later on. I will show you how, very elegantly, Mahler's formulation allows to take into account of this setting. So we said that instead of propagating the full posterior, we propagate the expectation on the full posterior, which is the PhD in here. So the prediction allows you to model birth intensity. Very simply, if you're having a body-worn camera, birth intensity means if I'm moving in this direction, it's very likely that all the new targets will come on this side. And so you can nicely model it with whatever function you think is appropriate for your application. The state transition is the product between how likely you think that a target will survive in that position of the state space, multiplied by the single target transition. So we are going back to what we like, the particle filter formulation, and we add around it everything that we want to add to make the formulation of multiple target tracking elegant and effective. The update, in this case we do have the last observation, is a function of how much you think that in a certain part of the state space you're likely to lose a target, the probability of missing detection. If you know how clutter looks like, you can add the distribution of the clutter, and that might depend on some classifiers you might have about your scene. And finally, you have the PhD likelihood, which is nothing else than the product between the single target likelihood and the function of the missing detections. Okay, so the beauty of this formulation is that you can incorporate all your difficult things of multiple target tracking in a simple and effective formulation, assuming that you know how to define these functions. Now, the last important bit that I mentioned earlier that we need to resolve is that of identity. How do we assign identity of everything that we have nicely cleaned through the PhD filter? In most cases, people do a clustering step of the particles after the filtering, and then you can use any mode-seeking procedure to try and find the peaks, and then you connect the peaks with graph matching or other solutions. What we have done here to try and get rid of the clustering, which is very expensive if you want to have real-time application, is to reverse a bit the way the filter works. So we move the association between the detections and the particle earlier on in the pipeline. And we have done something that is everything but rocket science. So instead of passing on to the filter the detections, we said, okay, sometimes I have some detections that I don't like, but I wouldn't really want to get rid of them because they might provide us some information that if I find some additional evidence later on, I want to resuscitate. So we define two classes of detections, the strong detections, those we are happy with, and some weak detections that we can somehow maintain a bit in hiding, and we will take up later on only if they are supported by some additional evidence. And that is an extremely simple idea that actually has increased in our method the performance enormously. That's one simple idea. The other very simple idea is that of, well, if you have a wearable cameras, you will have perspective distortions. So after a while, you can learn how people change in their height. And so we modulate all the variables of the predictions through what we expect to be the size of an object at that distance. And that as well is pretty helpful. So two very simple solutions here that have increased a lot the results in the MOT challenge. Actually, when we submitted to the MOT challenge at that time, this was the best performing online multiple target tracking algorithm. And then let's go back to the idea of strong and weak detections. So the strong detections are either linked to previous observations or are generating new targets. The weak detections are kept only if they are associated to a predicted old particle. So if we have a predicted old particles that in general would go to nothing, if we have in reality a weak detections that we wouldn't consider unless we have this prediction, well, then we await that and we use it over time. So these are the three elements of this multiple object tracker that again doesn't use any information about appearance. So if you want to use it with a Kinect, if you want to use it with any other sensors that provides you with a bounding box, this algorithm can be used as it is. So LiDAR, we said with LiDAR this morning, for example. Okay, so we work then a lot with this type of moving cameras. And we discover something that is obvious, but it's particularly interesting. So before moving on the developments we have done on hardware of this, I wanted to provide you with some experience that we will present in October at ICE. And it's, well, we need a lot of annotation when we want to evaluate those algorithms. And doing annotation is probably one of the most tedious activities we have in our job. So what people do is, well, I have a 50 frame per second, 25 frames per second. You annotate an object, then you skip 10, 15, 20 frames, you annotate another one, and then you do linear interpolation between the two, right? So it looks okay. However, when you start having moving cameras, this linear prediction becomes less and less appropriate. So we did a study of data sets that are available, and in some cases, 30, 40% of the annotation is linearly predicted. Now, if you have a tracker that is heavily reliant on linear prediction, well, that tracker will get better results than another one. If you're training deep learning models on an annotation that is generated in this way, well, your model will be heavily biased by the fact that the annotation was linearly generated. So a very simple, trivial concept. So we went and looked at ground truth that is available for public consumption, and we define a simple method to understand, to predict whether some annotations were linearly predicted. Based on that, we looked at what would have been the deviation in the performance scores that were being used, and through that we generated a confidence interval within which we don't really know whether that algorithm is better than another one. We apply that to some common tracking challenge evaluation, and in some cases, for some measures, the top 15 trackers were confused with each other. So you couldn't tell whether the number 1 and the number 15 were better because they were confused within this confidence level. Okay, so very simple concept, just be careful if your tracker is number 15. It might be as good as number 1. Okay? And I'm happy to discuss this later on if you're interested in more detail. Let's go back to our tracking problem. So the algorithm that I described earlier is running in this board that we use on board of mobile robots like UAVs and Kobuki platforms, and it's running in real time, as you see here, once your detections are given. So this is only the tracking part. And we use that for applications like this one. So we want to have assistive robotics application that could go from a shopping mall to a care home and other type of applications. So we want the robot to be able to follow a person that is being served, and therefore we need to be able to track that person and all the other people around. But we don't want to do this in a closed scenario like this. We do that in a crowded space, and we have set up a demonstrator where we have a number of static cameras that are communicated wirelessly with robots and have awareness about where all the robots and all the people are in this environment, so that the robots can change the way they move as a function of how all the other robots are moving. So it's a mixture between computer vision, communication, and distributed signal processing. And all that thanks to the fact that we have on board of these robots the Jetson with Wi-Fi communication. We do up here distributed signal processing together with the robots. So all the robots have got situational awareness of their space, and they can move around, avoiding clashing against other people and other robots. Okay, that's tracking and why tracking is interesting and very, very exciting. So there are a lot of applications that you can enable once you have physical awareness of where the moving objects around you are and where they are going. Now, we have heard this morning about re-identification in the case of vision. I'm going to show you a project we had recently, and we are now concluding, on re-identifying people that you see through a wearable camera. One will say, okay, that doesn't sound like a difficult problem. If you have a wearable camera, you recognize the face, you have that information, and every time you see that face, well, you simply say, okay, that's Francesca, that's Mohan, fine. However, wearable cameras are not as good looking, or they're not producing video that is good looking as the video I showed before. Because of course you don't have a viewfinder, so you're not selecting the proper spot. So this is an example of view. This is another example, right? So good luck with your facial recognition software there. And this is another example, nice face. So what we did in this case is we thought, okay, let's use audio information. Because we'll have situations where the video might be very good and the audio might be particularly noisy, especially if we are down in the street down here, and other situations where the conditions are the other way around. So our objective was to recognize the person being seen or heard from the camera under a very large variety of situations where both video and audio can be good, both video and audio can be bad, and any combinations of those. In the case of video, we have seen a number of backlighting, motion blur type of situations that are very common with body cameras. In the case of audio, you have reverberation, like a room like this would have a substantial amount of reverberation. If we go down in the street, we'll have a considerable amount of interferences from other type of noises. So if you then want to recognize the people you're meeting during the day and then somehow have a record or remember people you have met earlier or in previous days, then you might want to use either or both modalities so that you can enroll them quickly and then classify. So the easiest way to do it in the old-fashioned way would be, well, to extract features from video, extract features from audio, generate a joint feature vector, train a classifier, and classify then your results. Or if you want to use a deep learning pipeline, you will have an end-to-end training on the dataset. However, with the wearable cameras, we have still very, very, very small data sets, and we are not in a position to train good performing classifiers as we have in other types of applications for action rectification. Other ways in which we can go about this problem is, instead of having a early fusion to have a late fusion where we combine the score from the classifier. A third approach is that you have a mid-level fusion where the classifiers are talking with each other prior to taking a decision. And the fourth model is that where you have a hybrid approach where models somehow are talking with each other. They generate independent classification scores, and then the scores are combined in a smart way. The way we went about this problem was to use the results of each of the pipelines to influence the update of the model of the other modality. So we developed an approach that is generic for any modalities, and then we validate it with audio-visual signals, where in order to cope with the rapidly varying situation, so we don't have the luxury to have large data set to train our models, we want to be able to adapt the models to the situation we are in, of course, while avoiding to generate drift in the model or to diverge in a way that is undesirable from the initial model. So if theta here are the parameters of your classifier, and I and J represent the two modalities. In the case of audio and video would be A and V. The models at time t's will be a function of the model for that modality at the previous time instance, plus the current observation in that modality, and the classification result at that time of the other modality. So we use a form of unsupervised learning that is driven by a parallel classifier that is working on another modality with respect to the one I want to influence. Okay, sounds okay, with a big risk of drifting, of course. So we need a way to regularize this update to make sure that this update is not too abrupt, otherwise it will very quickly get off and diverge. And we have used this model in the framework of audiovisual re-identification, where we use a simple upper body detection and a histogram of colors to represent the video modality, MEL frequency coefficients, and the I vectors for audio. And then we use the simplest possible neural network to generate the results. And the core here is to use the results of the classification of one of the two modalities to influence the update of the other network in a way that if one modality is poor, the other modality can help adapting the model that is corresponding to the other pipeline. And in addition to that, we do a fusion of the score at the end. So this is working pretty well, especially in non-match conditions. So when you start having the first enrollment in conditions that are different from the one where actually you do your classification at the end. And interestingly, can be applied to other type of problems. And of course, if instead of having a very simple MLP, you have a more complex classifier, you can probably be even more effective in more complex scenarios. Now, so far, we have observed the world from a first-person vision perspective. Right? We said, okay, I want to track everything that is moving in front of me, or I want to re-identify people who are interacting or talking to me at some point in the day. Now, from now on, we will instead use the body camera to understand what the activity of the person with the camera are. So actually, you have this dual observation of the world from a body camera, the external and the internal. We will first look at activity recognition, and then in the privacy bit, we will look at activity recognition with other modalities in a way that we can preserve privacy. So, as I said at the beginning, first-person vision provides you with very weird ways of seeing the world. Some other works we have been doing and will be presenting at UCIPCO is how to evaluate the quality of the video from first-person vision, because sometimes you really have rubbish that you want to get rid of. Some other times you have quite a lot of information, like in here, about the activity of the wearer. And this data set that Girma, one of the former PhD students, collected is available if you want to play with that. What Girma did during his PhD was first to define robust motion features for this type of application. So what we want is to have an understanding of what the global motion features are, despite all possible outliers, so that we can understand what the activities of the wearer are. Then we grouped activities in the way that we could use a hierarchical classification in order to be more accurate in the decision. And what I will be talking about today is how to exploit 2D CNNs in order to classify temporal activities without the need to use and to train 3D CNNs through a cute way of stacking spectrograms of motion features together. And I will talk more about that. And then we will see how we use that information of the stacked spectrogram to transfer learning from video to inertial data. So trying to use the same type of classifiers for two different modalities in an economical way. And the data sets are available in our webpage. Who among you have processed videos from wearable cameras? So I get an idea. Okay, Paco. Okay. Did you enjoy? So you have a very wide selection of features you can use, right? You can almost use it as a coursework to understand well how to package features such that you can recognize global motion despite the presence of multiple type of outliers. So the simplest way and a very successful one is to use feature points, track them, and then you can characterize the motion. A number of successful approaches have used this optical flow as well. It's pretty expensive, but still by packaging optical flow, for example, using grids and histograms of elements of these grids, allows you to be able to characterize signatures of motion in a very effective way as well. And then, of course, an alternative is also that of having frame-based features like histograms of radial gradients and forms of CNN features, and then pool this information over time such that you extrapolate implicitly information about the time. And what Girma came up with, which sounds something pretty bizarre at the beginning, is to generate virtual inertial features from video. So you go from a very fat signal, that is the video, and you want to generate some signals that look like the signals of an IMU, a gyroscope. And if you do that, actually, again, it's probably not the most economical way to get that type of information, this type of information from wearable cameras, but it's pretty effective in combination with other features to discriminate between activities. A general framework, if you want to approach the problem of activity recognition of the wearer, is either to learn features with a deep learning method, or to use some combination of optical flow features and key points, and then somehow combine them, classify them, and take decisions. But the most important part for this type of pipeline is to understand how to use and to smooth information over time. And the way we went about it was to consider two stages of temporal information. One that is very compact, maybe a couple of seconds, and another one that is more longer term, that is connecting pieces of actions and smooths them over time. So for the shorter representation, we use this stacked spectrogram. I tried it. Stacked spectrograms over short temporal windows. And these spectrograms are generated by taking optical flow information, cleaned and smooth, organized into grids. You take each of those grids and you look at the vertical, horizontal displacement, and you take the Fourier transform of that over time. That information provides you with some data that you stack together in order to generate an image. Once you have generated an image out of those features, well, you can use a pre-trained model on ImageNet. And even if the semantics have nothing to do with the training set, it works. Yeah. And the main reasons for doing that is that instead of using a 3D CNN, you use a 2D CNN, which is much easier trained, especially when you have not much data. And then we take care of the longer temporal connections through an LSTM. And therefore, we have these two layers of temporal understanding. One that is at this very small clip of spectrograms, and the longer one for the LSTM. I wanted to show you the beauty of these spectrograms. So these are examples of features generated with those stacked spectrograms for going upstairs, actions, someone running, someone walking, someone either sitting or standing, and static ones. So these are the features that are given to the CNN in order for the CNN to try and understand the first-person vision activity of the wearer. Then, and this is happening in here, we have a longer-term inter-sample smoothing through the LSTM. So I think the interesting aspect here is how to package motion information in a way that it will look like an image. And to get there, you need to do some translation, scaling, resizing. But I think that the main message is there. And then, surprisingly, images like this can be classified very easily with the pre-trained models. Now, if you have a wearable camera, you are likely to have access to other type of sensors. We have seen earlier that you can use a microphone, but wearable cameras have also got IMU data. So can we transfer what we have learned from vision in that case to IMU data? So the answer is yes, with exactly the same structure we have seen earlier, but we have applied to another data set that we collected in collaboration with UBC in Barcelona, where the idea was actually to come in the area of this symposium, which is trying to understand what the motions of a person are. In this case, Andrea was wearing some heavy shoes in order to simulate the movement of an older person. And so what we wanted to do is to use IMU data, in this case for the specific applications that we're interested in are here at the knee level, and the camera here, and somehow make the signals between these two sensors communicate with each other in order to improve the quality of the classification. And so we have a video here, IMU data there. Each of them goes through a separate pipeline with the different steps that gets together only at the level of the LSTM. So I want to show you here a case of stacked spectrogram for the IMU data. So these are horizontal, vertical, and direction components of your IMU data. This is the way that through a fast Fourier transform, these data are presented as a spectrogram. Through scaling and normalization, you get this result. And then we pretend that these three planes are planes of an image. And this is what you get out of 3 seconds of your data. And that's at this level. Then the CNN is applied, classifier, they are combined through a sparsity measure, and then the LSTM, and then finally the wrapper. So here the main message is, in order to compensate for the problem of lack of training data, we can take our problem and transform it into a problem for which we have already a number of trained classifiers. Our life is easier, and results are surprisingly good. Last part of the talk is, oh yes, okay, we have these wearable cameras. We have, of course, the problem of privacy of people who are imaged from their cameras, and we have worked on that, but I will not cover this today. What I will cover here is the idea of having an application like activity recognition of the wearer, where we want to give access to an app to the signals generated by the sensors that we are wearing, but we want to allow the app to be able to recognize only the activities we have subscribed for and to have information about us that we want that to be or to have. And in particular, we look at the problem of recognizing activity without disclosing gender. Yeah, because of course, if you start looking at how a person moves, it's probable that you can tell what is the body shape of that person, the size, the height of that person, the gender of that person. And what we want to do is to try and provide a new set of data to the app that are modified in such a way you can satisfy your application, but not leak data that you consider to be sensitive. So the goal is to share a transformed version of the sense data. The solution is an architecture that takes the data once you know the type of inference you want to have and modifies that such that the level of accuracy of the activity recognition is maintained high and the probability of recognizing the gender is maintained low. The probability of recognizing the gender is maintained low just by pushing the gender classifier to go to 50%. So it's very simple. Right? So we say the goal of our gender classifier is to go towards 50%. The goal of our activity recognizer is to stay as high as possible. And we came up with the GEN, which is a guardian, estimator, and neutralizer. It sounds very fancy and nice to close the presentation. So the guardian is actually the core of everything and is the object we produce after the training and is the object that is used to transform our input data to what we provide to our service provider. The estimator is the part of the system that checks whether the data that are generated by the guardians are modified well enough to maintain the accuracy high and the inference on sensitive data low. And the neutralizer is that what uses the output of the estimator to modify the guardian, which in our case is an autoencoder, such that you will change the data such that the constraints we mentioned are satisfied. So the example we have verified this architecture for is recognition of 4 activities without disclosing gender. And we have generated a data set that is publicly available. There will be a link later on, where 26 people have worn a mobile phone very close to their body, have done 6 activities, and the idea was, well, if I get a certain recognition accuracy disclosing gender, will I be able to remain very close to that recognition accuracy when gender is not recognizable? And the way the guardian is trained is through the estimator. So the guardian is receiving the input data. These are multiple data over time, passed on to the guardian, that is the autoencoder, that is moving on the data to the estimator, which is a multitask CNN that is generating as output the activity and gender. The neutralizer is a hybrid loss function that is looking at the maximization of the activity and the minimization of the recognition for gender. And again, if someone is interested, I can show you how in practice we do that. The results of this training generate a guardian that has been modified, that has been trained in such a way that the input data are modified so that an estimator then will be able to perform well for activity recognition, but don't disclose the gender. And this is an example of results. So motion sense is the data set we have collected that is available in Mohammed GitHub page, and Mobiac, which is another one. So this first column provides you with the results of activity recognition prior to the modification of the sensing data. So you have 95% in recognition of the activity, 95% in recognition of the gender, and so on and so forth. As with HAT is the sensing data that have been modified by the system, and you can see that there is a decrease in a few percentage points in here and in here, whereas gender recognition has reached the level you wanted, so confusion around 50%. So if this number in yellow is around 50%, we're happy. If this number in yellow is very high, it means that with a high probability, the system will be able to recognize a gender. So you can see that the transformed data doesn't change dramatically the activity recognition results, and it's a trade-off between privacy and utility of the service you're using. I think it's a pretty interesting way to adapt a system not to blank out data prior to pass it on to a service, but to modify the data, knowing phone, for example, you're not giving access to all the raw sensor data to the system. Okay, and with this, I'm done. Just summarizing very briefly. The first two parts of the presentation were about looking the world from a first-person view, and in particular, understanding the motion of the objects around you, or determining which people you have met during the day. The second part of the talk was about recognizing the activity of the wearer, either through video or through video and IMU, and at the end, how to modify the sense data in such a way that you can protect some sensitive information while still enabling the services that you want to obtain from your app. And these are the names of the people who have done the code for these projects, and I thank them very much, and thank you very much for your attention. Thank you.